Good evening. Welcome to today's session. Today is the 10th week of the problem solving session for this course. Uh, so we'll be dealing with problems from the lecture series from 45 to 49, which is going to be helpful in solving the assignment 10. The due date of assignment 10 is tomorrow, 2nd of October. So like usual, I'll be displaying questions. You need to put in the answers in the chat box. And after that, we'll be discussing the solution or the explanation, whatever it is associated with that question. So we'll move on to the first question. Which out of the following is also known as the structural measure in scientific management of groundwater resources? Are these the demand side measures, supply side measures, scientific measures, or none of the above? You can drop in your answers in the chat box, and then after that, I'll go into the explanation. Okay. So this week's portion is largely based on groundwater and groundwater resource management and the latest, the management, irrespective of whether it is groundwater or surface water or any kind of resources, has to be maintained or managed in a scientific manner that is taking care of the resources in a sustainable way. So any strategy for scientific management of groundwater resources involves two categorization of management techniques. One is taking care of the supply side, and the other is taking care of the demand side. The supply side is nothing but all those management techniques that involve fulfilling the supplement of this groundwater resources to its end users. That is increasing the extraction of groundwater, improving the quality of groundwater that is being used by the end users, and so on. Whereas the demand side measures is taking care of how the groundwater resources can be managed in such a way that it is available for usage to all of the people or all of the end users in in whichever way they require it to be used. So this will involve techniques that control the extraction of groundwater, protect the quality of the groundwater, and overall conserve the groundwater resources. Now, these supply side measures, which is basically managing how we can utilize or how much of water can be extracted in a sustainable manner, is also called as the structural measure. So the question here is, um so these are some of the uh, categorization into a supply side management is done by categorizing the terrain or the area based on its topography. Then rainwater harvesting and artificial recharge are some of the scientific management techniques that are used when it comes to the supply side measurements. The demand side measurements, on the other hand, is focusing on the proper utilization of the resources so that it is available for a longer period of time. The sustainably utilizing the groundwater resources. And for that purpose, it is necessary that in order to fulfill the duty or in order to exercise judicious utilization of the resources, one must take ownership of the groundwater. Now, the groundwater resources, uh, an idea or a thought or the responsibility of considering groundwater as a resource, not just as some random resource, but it is our own. It is something that we have to value, something that we have to use it in a very careful manner, indicates that you need to take ownership of the groundwater. Again, there has to be management techniques that focus on allocating groundwater resources as per the requirement, and also in order to bring about a regulation, price the groundwater so that there is effective utilization without wastage. Then again, these management techniques, once it involves the stakeholders, the people who are benefiting out of this groundwater, if it involves stakeholders in the process of management and planning and conservation, then again, this is a scientific measure that will help in conserving the resources or help in implementing judicial, judicious utilization of groundwater. So these are some of the demand side groundwater management techniques or important factors that need to be considered when demand side groundwater management uh, is considered. Now, so there are two categorization of scientific management of groundwater resources. One is the supply side management, and the other one is the measures taken to see how the demand factor of the groundwater resources are managed. So the question was, which out of the following is also known as a structural measure? Again, the supply side measures are also called as a structural measure. So option B will be the correct answer for this question. Moving on to the second question. According to the This is the second question. According to the most recent guidelines established by the Central Groundwater Authority, industries are required to construct a groundwater monitoring telemetry system based on how much volume of water they are extracting. So, if they are extracting a particular threshold of groundwater, then it is mandatory that they use or they set up a groundwater monitoring telemetry system. uh, the industries have to do this. So, what is the threshold volume of water for which this system has to be established as per the guidelines of the CWGA? Okay, moving on. So, the Central Groundwater Authority is the ministerial body that sets guidelines, that sets regulatory measures, and all sorts of management, planning, approvals related to the groundwater resources. And it has made, according to their guidelines, it is mandatory that industry set up a groundwater monitoring telemetry system if they are extracting more than 10 cubic meters of water. So the correct answer would be option C, 10 cubic meters. The groundwater monitoring telemetry system is something of the that is set up by the CWGA is something of this sort. So they have a mechanism to uh, measure the flow rate of the groundwater that is being extracted, and according to that, it is connected with an IoT system that will take that will send the reading to a cloud, and then based on that, a monitoring will be done. So this is just a framework of the groundwater monitoring telemetry system uh, that is suggested by the CWGA. Moving on to the third question, which of the following is a major source of groundwater recharge? Is it rain, river, pond, or lake? Which out of the following is one of the major sources of groundwater recharge? Okay. So the answer is rainfall. The question asked here is the major source of groundwater recharge. Apart from rainfall, even rivers and lakes and ponds can uh, help in recharging groundwater, where we have studied about the influent streams and effluent streams. And that influent streams are the streams that provide water into the groundwater aquifers. So they also can help in recharging groundwater, but the major source of groundwater is rainfall. We also studied in the last session, or the last bunch of lectures is focusing on how confined and unconfined aquifers are receiving its water, how unconfined receives its water from direct rainfall, the percolation or the percolation of rainfall, whereas unconfined aquifer, they are not getting a direct recharge of water from rainfall. Instead, there's one end of the confined aquifer, which is an unconfined aquifer. They will get the water recharge, and it is from there that the confined aquifers are getting water. So here in this question, the major source of groundwater recharge is rainfall, although all these sources also help in recharging groundwater through the influent stream system. Good evening, Hanmanta. Now the fourth question, how much area in hectare is called a watershed? Is it 10,000 to 50,000 hectare, or 50 to 1 lakh hectare, or 50 to 2 lakh hectare, or 1,000 to 10,000 hectares? Okay, so let's just see how watershed is classified based on the area in hectares. So as you can see here, you call a basin or a catchment a watershed when it has an area extending from 50 to 2 lakh hectares. Then when it is extending from 10 to 50,000 hectares, it is called a sub-watershed. Watersheds of the area 1,000 to 10,000 is called milli watershed. Lesser than that, 100 to 1,000 is called micro watershed, and 10 to 100 is called mini watershed. So our question here is, which category of area falls under the classification watershed, which is 50,000 to 2 lakh hectares. So you need to keep in mind this classification. A bunch of questions, maybe one question can come from this. So the correct answer is option C, 50,000 to 2 lakh hectares. So let's go through this classification once again. 50 to 2 lakh hectares come under watershed, 10 to 50 under sub-watershed, 1,000 to 10 under milli watershed, 100 to 1,000 under micro watershed, and 10 to 100 under mini watershed. So the smallest classification is mini watershed, largest classification is watershed. Again, how much area in hectares is called a micro watershed? So we just now learned about the area coming under each classification, so it will be quite easy for you to. Okay. So the correct answer is option C. 10 to 1,000 will be mini watershed, 100 to 1,000 micro, 1,000 to 10,000 milli, 10,000 to 20,000 sub, and 20 to 10,000 to 50,000 sub, 50 to 2 lakh is watershed. Now we had talked about supply side and demand side measures. So what are the major goals of the supply side measure for scientific management of groundwater resources? We briefly went through what are the different what are the different strategies that are adopted in scientific management of groundwater resources. What is supply side management? What is demand side management? The question here is, what is the objective of the supply side management? So let's see, supply side management is mainly development of additional groundwater resources in order to fulfill the supply side of the groundwater resources. Excuse me. So through artificial recharge, rainwater harvesting, and any technique that helps in recharging groundwater comes under the supply side measure. So it is maximizing the availability of groundwater and also aiming at increasing the extraction of groundwater is what is the supply side measurement measures are focused on. So controlling groundwater resources will come under the demand side measures. Again, protecting is coming under the demand side measures. Anything related to conserving groundwater resources, protecting, controlling, uh, restricting, everything is coming under demand side measures. Whereas increasing the intake, increasing the extraction, making more water available to the end users, all of these will come under the supply side measures. So option C would be the right answer, increasing extraction of groundwater based on its availability. Wastewater return is an example of indirect recharge. Is this true or false? Okay, so the answer is false. If you look here in groundwater management, there are three ways in which groundwater can be recharged. One, naturally, we had learned in the last class about natural ways in which the groundwater is recharged. Then there are artificial methods, and there is also an indirect recharge through acutard leakage. So the unconfined aquifer, if it is its bottom is consisting of a acutard bed, then the seepage is possible. Acutard is nothing but a geological formation that can store water, and it can also transmit water, but not as significant as that of a aquifer. And so majorly the seepage or vertical leakage of water is happening through acutards. So Acutals is helping in indirectly recharging this aquifer storage or groundwater resources. Natural recharge includes if there's excess rain through infiltration and percolation, directly water is being recharged. And then artificial recharges include in canals and all, if lining is not then the water there can help in mm, recharging the groundwater. Wastewater returns. It's not the direct wastewater, but wastewater that is processed. These wastewaters can also be used to recharge the groundwater resources. So indirect recharge is acutard leakage. Artificial recharge will involve wastewater return. So here the correct answer is option B. A wastewater return is an example of artificial recharge, not indirect recharge. Again, based on the scientific management of groundwater, which of this does not fall under the demand side measures? We checked out how what categories of management techniques focusing on what is under supply side and demand side. So in these, out of these four, which of the option doesn't fall under demand side measures is the question. Okay, so again, once again, to just brush up through that, supply side measures are involving those techniques or those management strategies that involve in increasing the extraction of groundwater, increasing the extraction, making more groundwater available. Whereas demand side is what is curbing the usage of groundwater in order to preserve, protect, control. Whatever restrictions are being assigned as a part of preserving groundwater, then those will not come under demand side. So judicious utilization of management to ensure long-term sustainability is coming under demand. Then taking ownership of the groundwater is also coming under demand side. It is one method through which we can develop the sense of responsibility to conserve groundwater. Then need-based allocation pricing of resources. So uh, according to the type of demand or requirement of groundwater resources, allocating prices to the resources is another way of demand side measures. Extraction of groundwater focuses comes under the supply side measure. So demand side measures includes ownership, taking ownership of groundwater, need-based allocation, pricing of resources, involvement of stakeholders in various aspects of planning, execution, and monitoring, and effective implementation of regulatory measures are considerations with regard to demand side demand side groundwater management under the scientific management techniques. So the correct answer is option D. Moving on. Chlorinated hydrocarbons is a qualitative issue in water resource management. Qualitative issue deals with the quality of groundwater. Quantitative issue deals with the quantity of groundwater. So, what kind of issue is the presence of chlorinated hydrocarbons? So, the management techniques of groundwater resources majorly not only just groundwater, any resources management of resources is focused on adopting sustainable management techniques, which is nothing but the being able to use the water resources for our requirements, as well as controlling the usage in such a way that sufficient resources are available for the future generations as well. This is what is basically the principle of sustainable management of any kind of resources. When it comes to water resources, there are some non-sustainable practices involved that includes quantitative as well as qualitative non-sustainable practices. Non-sustainable practices are practices that results in an overexploitation of the resource. Now, since we are talking about groundwater over here, it is overexploitation of the groundwater. So, some non-sustainable practices that will affect the quantity of groundwater is excessively pumping out the groundwater more than what we require. Then destruction of wetlands. This is again going to deplete the quantity of groundwater. Then salinization of soils is again going to make groundwater very unfit for use. So hence that part of the quantity of groundwater that can be used is going to go down. Now, some non-sustainable practices that can result in degrading the quality of groundwater is again contamination through salts, chlorinated hydrocarbons. Again, salinization of soils is also one technique which will result in the degraded quality of groundwater. So, chlorinated hydrocarbons is a qualitative issue that is affecting the quality of groundwater resources. So, the answer for this question would be true, because it is impacting. Chlorinated hydrocarbon is a pollutant that impacts the quality of groundwater resources. So the answer for this question would be true. Now, which we just looked at some non-sustainable practices that are qualitative as well as quantitative, qualitative as well as quantitative, uh, reducing the quality and quantity of groundwater resources. Now, the question here is which is not a quantitative, uh, non-sustainable issue of water resource management? Which out of this is not a quantitative practice? Is it overpumping, destruction, contamination, or none of the above? Okay. So we had studied about the quantitative non-sustainable issues of water, which includes destruction of wetland, then over pumping, salinization of soils, etc. So over pumping, destruction and all come under quantitative. They're asking which is not a quantitative. Contamination of water resources is impacting the quality. So it is a qualitative issue. So correct answer for this question would be option C. Which is the first state in India to have made rooftop harvesting structures compulsory for all the houses across the state. So it is Tamil Nadu. The government implemented this policy in 2003, where it makes a rooftop harvesting. When a house is being constructed, it has a concrete roof, then it is necessary that rainwater harvesting structures be compulsory. Rooftop rainwater harvesting structures be compulsory. The correct answer is option C, Tamil Nadu. Moving on. Again, which out of this is not a qualitative issue regarding non-sustainable practices of groundwater? Or yeah. Question asks is not a qualitative. Okay. So again, contamination impacts the quality. Chlorinated hydrocarbons impact quality. Salts also impacts quality. Overpumping is a quantitative issue. So the correct answer will be option B, overpumping. Next question, which out of the following is a conjunctive use program in groundwater resource management? So the correct answer is option C. Conjunctive use is nothing but a combination of surface water and management of surface water and groundwater resources. That is, this way you can conserve the surface water as well as it helps in conserving the groundwater resources. That is what is called a conjunctive use. It is a combined technique for management strategy for saving surface as well as or using surface water to help in replenish or recharge or save groundwater resources, or a technique which will maximize surface water as well as groundwater. So, combining the surface water and groundwater, any management technique that is associated with combining surface water and groundwater or management of surface and groundwater is called conjunctive use techniques. So, storing surface water into underground formation is an established practice in the conjunctive use management techniques. This is also an artificial method to recharge groundwater. Now, another artificial method is the making seawater barriers. Seawater barriers are made in order to protect coastal aquifers, which might get contaminated because of excessive salt as a result of seawater intrusion. When the existing or the persisting problem of seawater rising will result in this seawater to diffuse into the groundwater, and the groundwater will become salty, or the entry of salts into groundwater is going to contaminate the groundwater. So in order to protect these coastal aquifers from the seawater intrusion, there are structures called seawater barriers that are made in order to stop the seawater from mixing with the groundwater. So this is another artificial uh, protection technique to protect the groundwater resources in the coastal areas. The conjunctive use program involves storing surface water in as that can be used as groundwater for future. Then, yeah. So these are the two important points here. So following is a conjunctive use program in groundwater resource management. It is storing surface water into underground formations. Rainwater harvesting is an artificial recharge technique. Lining of canals is also an artificial recharge technique. So correct answer will be option C. Which of the following is a major step involved in watershed modeling? Excuse me. So sorry for the clarity of the things here enough. So watershed modeling is nothing but it's nothing but um, creating a model that mimics a watershed so that we are able to predict or estimate the various hydrological components that is contributing to water flow in that watershed. Now, watershed models involves, and it is a very complicated process, or developing a watershed model is a very tedious procedure because it involves natural components like rain, infiltration. All of the hydrological components are natural processes that has got high variability. So, the first step into developing a watershed model is to create a model that involves methods or equations or quantifying the hydrological components in a watershed model. So, how much rain is occurring? If there is an equation to formulate the amount of rainfall, then the water budget equation to estimate the infiltration, equation to estimate evaporation. All of bringing all of these equations together and interlinking them with each other will result in the formation of a watershed model. Now, after this watershed model is developed, we have to see if this watershed model is accurately representing that watershed. Is it able to predict the results which are the same as what is happening in the watershed? So, for that, there is a process called calibrating and validating the model. Calibrating the model, some we can actually put in some values, assume some values, and see if that assumed value is predicting results which is in close to the real scenario. Then keep changing the values and find out which is the most apt value that will help in predicting results which are closer to reality. That step is called calibration. Then you do validation. You will see if when this calibrated value is able to generate results which are closer to reality. After that, when we know that this model is final, we can use it for predicting results. We can see that depending on the data that we have now, 10 years later, what is going to be the rainfall, what is going to be the floods or droughts or any kind of hydrological process. So that is what watershed modeling is. It involves formulation, calibration, and then application of the model. Now, what are the main structure? What is the basic constituents of a watershed model is the input function, how much water is entering the system, output function, all those equations that simulate the how much water is exiting the system, and transform function is between this input and output function. How is uh, the hydrological process or water changing from this input form to output form? What are the equations that are involved in that? So these are the three main constituents of the watershed model: input function, output function, and the transform function that can convert the input into the that is responsible for the input to become the output. So our question was, which of the following is a major step involved in watershed modeling? Formulation is a major step. After that, calibration or verification is a major step. Application is also a major step. So the option D, all of the above, is the correct answer. Moving on. The Urate hydrograph is an example of what kind of a watershed model? Is it a distributed model, lumped model, black box model, or does it come under all categories of models? Okay, so let's just see what these models are. So we just talked about what watershed modeling is, how is a watershed model made and all. So watershed models can be broadly classified into three categories. One is black box, one is lumped, one is distributed. Excuse me. Okay. So black box models are models that will mathematically represent the relationship between rainfall and runoff. There is no equation based relation. It will take the data of some 10 watersheds. We'll check what is the rainfall. We'll check what is the runoff. And we'll say that rainfall is this many times runoff, or runoff is equal to this many times rainfall. It is finding out or describing the relationship between rainfall and runoff in a mathematical, it is bringing a relation between these two based on a lot of data. But how is the process happening is not described in these models. That is, there is a physical equation associated relating, if there is a physical equation associated with relating rainfall to runoff, that is not available in these kinds of models. So, unit hydrograph is an example of such a process or such a model. It is a black box model. Now, there is another category of model called distributed models, which are very complex. Every process is described by a set of physical equation. It is an equation-based model where all the processes, rainfall, rainfall, occurrence of rainfall, the movement of rainfall, the the movement of water, infiltration, evaporation, every process involved in that the model takes care of is described using proper physical-based equations. Such models are called distributed models. Um, and then there are lumped models, which is having one portion of relationships, random relationships or empirical relationship between hydrological components, and then again some part of it involves physical based equations. So unit hydrograph comes under black box model. Stanford watershed model comes under lumped model. Distributed models are any model that is based on flow equations is a distributed model. So here the question was, what is a unit hydrograph? Under what category does it fall? It comes under the black box model, which is option C. Which out of the following is not a major objective of the integrated watershed management approach? Okay, I don't think, let's get familiar with this integrated watershed management approach. So integrated watershed management approach is nothing but when you consider when you consider managing a particular resource like groundwater, it is not sufficient if you just uh, make management techniques that will only help in preserving groundwater without taking into consideration surface water or without taking into consideration the population, without taking into consideration the kind of terrain, or without taking into consideration the economics of the city of the place where the groundwater is available. So all of these factors have to be considered when we are moving into management of any kind of resources. So in terms of groundwater resources or surface water resources, management of water in a watershed has to take care of multiple uses of the water as groundwater, as surface water, based on the sources from where all the water is. What are the various uses of water? What is the kind of population that is using the water? What kind of land is available? What is the kind of income generated by people there? What is the cost of water there? What is the cost of supplying water there? All of these have to be taken into consideration when we are devising a management technique. So this approach is called the integrated watershed management approach, which is taking into consideration several factors and not just water element as alone. So water should be managed at the lowest appropriate level. That is, every sector that is that is utilizing water has to be taken into consideration. What is the smallest use of water? What is the basic community that makes use of water? Every strata of the society as well as every particular usage of water has to be taken into consideration. It should take into account all of the interests of uh, for any person or any living being that is making use of water. All of that factors have to be involved when you make a management technique, and also it has to be treated as a valuable product, an economic good. So it is only then that we can develop an appropriate management approach. So the objectives of integrated watershed management approach is taking, giving or considering the multiple uses of water, taking care of water at the lowest appropriate level, then taking into account all of the interests of everything and every being that is making use of water, and treating water as an economic good. So out of this, water allocation should be localized. Is not a objective of integrated watershed management. It has multiple uses, so it has to be managed in an integrated way. Should be managed at the lowest appropriate level. Also take into account the interests of all who are affected. These are the various objectives of integrated watershed management. So option D will be the correct answer. Now we got an idea about what integrated watershed management approach is. Which out of these following is not a strategy? Which out of these following do you think will cannot be a strategy involved in integrated watershed management? So, to implement integrated watershed management, one of the strategy is the long-term sustainable future, making water uh, a long-term, making the availability of water a long-term viable sustainable future for basin stakeholders, non-equitable access to water resources for all water users. Excuse me. The application of principle of demand management for efficient utilization, prevention of further environmental and the restoration of degraded resources. Which out of the following do you think is not a strategy that is adopted for integrated watershed management? I'll move on to the answer. So the various strategies that are adopted in integrated or followed in integrated watershed management approaches, uh, making it a priority for the future. Whoever is making use of this water, it has to have a sustainable future, and not only the availability, it should also improve the economics of the community that is making use of the water. It is making it very useful for the environment in such a way that people can keep living there using the water, as well as save water and land for the future generation, and restrict or reduce the degradation of the resources. So making it developing a strategy that is sustainable for whoever is using the water resource in that watershed is one strategy adopted in integrated watershed management. Not just usage, but improve the quality of life, improve the quality of resource, improve the economics of the resource. Everything is involved in that. That is what is called making the water a viable, sustainable product for the future. Then another strategy is giving equal access of water resource for all of the users. That is another equal access means, suppose say the domestic requirement and the industrial requirement are going to be different, but just because industry people require more water, it doesn't mean that that same amount of water be provided to domestic users. What is the requirement sufficient? If the domestic people require this amount of water, then all the domestic users need to be provided with that quantity of water. Similarly, standardizing or making accessibility to this water resources based on the requirement is another strategy that is coming under the integrated watershed management approach. Then applying the principle of demand management for efficient utilization. Principles of demand management is nothing but uh, uh, is there is there enough sufficient supply of the resource according to the requirement or demand, and aligning these two factors, aligning the demand and with the supply is what is the basis of principles of demand management. Say suppose if the demand is very high and the resource is very low, then reducing the demand so that the reduced supply can meet the requirement, and such management or such techniques adopted is all based on the principles of demand management. So that is another strategy that need to be adopted in integrated watershed management. Then prevention of degradation of the resources, short term as well as long term, is another strategy. So in here, non-equitable access to water resource for all water usage is not a strategy adopted. Equitable access to water resources for all water usage is what is the correct answer. So option B will be the correct answer in this question. Next, which of the following is an example for indirect recharge of groundwater? We have gone through this portion in the earlier slides. It will be okay. So we had gone through this portion. Indirect recharge involves acute leakage. This is one source of indirect recharge of groundwater. These are some techniques of artificial and natural recharge. Excess rainfall, surface water seepages and all coming under natural recharge. Irrigation losses, wastewater returns are coming under artificial recharge techniques. So the correct answer for this question would be option C, acotard leakage. So maybe we'll take a 2 to 3 minutes break now. The time is 6:54. So we'll be back at uh, exact 7 o'clock. Until then, you can go through this question and put in your answers. We'll be back by exact 7 o'clock. Okay, so let's continue the discussion. Which of the following is not a groundwater management technique? Conjunctive use of surface water and groundwater, artificial recharge of groundwater and seawater, over pumping of groundwater, intra-basin transfer of water. So the various correct answer, both of you, is C. So various groundwater resource management techniques involved conjunctive use of surface water and groundwater, which I had explained earlier, combination method. I mean, making use of surface water to save groundwater. Artificial recharge of groundwater that involves lining of, uh, recharge through line when the canal seepage through canals, rainwater harvesting and all are artificial recharge. Seawater barriers are another technique. Interbasin transfer, intra-basin transfer, indirect recharge through avoidance of pumping. So one indirect recharge technique is when acute leakage is occurring. Another one is when you don't pump water itself, the water is going to get accumulated and it is going to recharge. And the other technique is control well fields. We'll go into the 3, 4th, and 6th one in detail. So the answer for this question is option C. Overpumping is not a groundwater management technique. In fact, it is a groundwater exploitation method. Overpumping of groundwater. Now, wellhead protection strategy falls under what kind of groundwater management technique? Does it come under interbasin transfer, intrabasin transfer, artificial recharge, seawater barriers, or control wells? Wellhead protection strategy. Okay, so we saw about different methods of groundwater recharge. Here we we are talking about control well fields. Wellhead protection strategy is based on control well fields. Control well fields are nothing but when you strategically place wells, which are basically called control wells, in order to control the direction in which the groundwater flows. Then such wells are called, the strategy adopted is called wellhead protection, and technique is called the control well fields. So what happens when we place wells in a manner that it can alter the flow of groundwater, or it can result in the flow of groundwater in a particular direction, because the hydraulic gradient will change as a result of these wells being placed in a particular interval or particular um, particular interval basically. Then this technique is called ground control well fields, and the strategy is called wellhead protection strategy. So this is what control well fields are. The answer for this question is control wells. Now there is option D. There is something else called interbasin transfer also, and intrabasin transfer. So intrabasin transfer of water is nothing but when we effectively find techniques to say within a basin there are several water bodies, rivers, streams, ponds, etc. When one water body is depleting of it, is undergoing a depletion of its resources, then utilization of the water available in another water body within the basin itself is what is involved in intra basin transfer of water. This is less expensive. There is something called interbasin also. So here it is less expensive than the interbasin transfer because it is within the basin itself that you're transferring the water. One area has an overdraft that is actually having excess of water. So this areas that are having excess of water can be utilized to recharge other places where the water is less. So this is what is the basis of intrabasin transfer of water. Interbasin transfer of water is when the same thing that we have described in intrabasin, it is occurring between two different watersheds. So there we are talking about one single watershed, water bodies within one single watershed. Here we are talking about the transfer of water or recharging of water from water bodies that is present in another basin to supplement the water availability in a different basin. This is a very complicated process. Includes moving water from two basins, administrative boundaries, and it is a very costly affair. So it's about interbasin and intrabasin. Then we looked into artificial recharge and seawater barriers. So that was about the question was about wellhead protection strategy. It is falling under control well fields technique, intrabasin, artificial recharge, and interbasin transfer. We all went through what all these three means. Next question: which technique is used to protect coastal aquifers against seawater intrusion? This is also something that we went through. So correct answer is seawater barriers. We had talked about this earlier. When there's seawater intrusion, then ridge-like structures are constructed so that the coastal aquifers are not contaminated with the salt water from the sea. Then next question, which of the following is not a reason for the need for management of groundwater resources? Which is not a reason for groundwater management? So yeah, the requirement or the necessity of management groundwater resources majorly is because the world is facing a huge scarcity in the groundwater resources. Then again, another reason to manage groundwater resources is because of the pollution that is being experienced by groundwaters. Then groundwater is often mistaken to be considered, I mean, it is said as it is talked about as a renewable resources, but considering the rate at which it is being used or exploited, it has to be considered as a non-renewable resource. So that is one reason why we have to manage our groundwater resources. And then to meet statutory regulations, we need to have proper management techniques. So this point, whether groundwater is a renewable or non-renewable resources, there's an excessive utilization of water more than what is required, or exploitation of the water, because it although we have groundwater resources contribute to a huge chunk of water availability, only less than 6% of the utilized water is being replenished during an entire lifetime of a human being. This is because the rate of flow of groundwater takes a long time. It might be flowing at a rate of very slow rate of flow of groundwater is occurring. So replenishing the water that is utilized is at a very slow rate. So often this has to be, or not often, mostly this has to be considered as a non-renewable resource, because for the quantity of water that is utilized by, say, per capita is not being replenished by that person. If you are tallying the utilization and replenishment. So that is why we say that groundwater, although it is consisting of water and water is always persisting in some form of or the other, it has to be considered as a non-renewable resource, because only very little percentage of the utilized water is being replenished. So groundwater is a renewable resource is the wrong point in here. All the other remaining 3 points are reasons why we need proper groundwater management techniques. Moving on. Which technique of management of groundwater is involving storing surface water into underground formations for future use? Correct. Artificial recharge of groundwater. So we talked about something called conjunctive use program. So conjunctive use of water. So storing surface water into underground formation is one form of artificial recharge. So the correct answer here is option C. Now we are moving onto something called the groundwater resource development. Let's just go through it once and then we'll come back to this question. So there are various stages of groundwater resource development when you take into consideration a major aquifer. The stages can be represented like this: the baseline situation, then there is the incipient stress, significant stress, unstable development, and the stable development. So what does this mean? So if you see this plot, you can see that there is one line that is representing the sustainable level of resource development with acceptable impacts under present conditions. So here it is not an unrealistic approach. It is taking care, it is making sure that the utilization of the resources occurring at a sustainable level, and with uh, while also considering the impact of utilizing, if it is bringing about some conflicts or degradation or any such problem, it is also taking into account of all of that, and then forming a threshold for this usage, and it is based on this threshold that these stages are defined. So if the total extraction of water uh, is if it is coming within this sustainable level of resource, then it is a fine it is an acceptable stage of development. But say in this case, you see a peak here where the extraction is exceeding the sustainable use of water, which will indicate that this stage is not a very good stage of development of management, groundwater resource development. So what are these baseline situation, incipient stress? We'll go into that. So baseline situation is when you have adequate uh, quantity as well as quality of groundwater. So if you are in a state, if you're in a place and the availability of groundwater is in excess, the quality of groundwater is also very good, but the requirement of water is not as much as the supply is available. So there is no much requirement of the water, but the resources available in plenty, the quality is very good, and then there are no much issues that is associated with using water. Then that is called the baseline situation. Now there is a development stage where which is called incipient stress. What is happening? The availability of groundwater is water is available, but the usage is increased. As a result of this, small conflicts are arising between the people who use. Then this stage of development is called the incipient stress. Now, a significant stress is when you say that this abstraction or the extraction of groundwater has rapidly increased, and this is as a result causing a depletion in the resources, and also there are a lot of other problems or negative impacts that is associated with the extraction of this groundwater. Then that stage is called a significant stress. So there are some frameworks, there are some management techniques that have to be implemented based on at what stage of development the groundwater resources are according to this categorization. Now, unstable development is when there is uncontrolled extraction of groundwater, the groundwater resources are getting depleted. There is a huge conflict between people who are utilizing this groundwater. Then that stage of development is called an unstable development. Then there is a very stable, highly developed developmental stage where there's sufficient abstraction, but then the groundwater resources are not getting depleted. There is no problem between the stakeholders, neither is the quality of groundwater going. So this is because there's a very good management technique implemented over there that is taking care of the needs as well as not depleting the resources as well as not contaminating the resources. So such a stage is called highly developed stage. So when you look at this graph over here, you see that this 3A, which is an unstable development, is going into a state above the sustainable level of resource development, as a result of which this stage is a very unstable stage and a problematic stage. Now, whereas this 3B stage is able to control the usage of this groundwater within a sustainable level. So this is a very highly developed stage. So this is how the categorization of the development of groundwater resources are done, and it is based on the stages of development that the management techniques are implemented. So the question was, which stage of groundwater resource development represents excessive uncontrolled abstraction with irreversible aquifer deterioration and conflict between stakeholders? This is the incipient stress, unstable development, stable, highly developed, or significant stress. 0, 1, 2, 3A, and 3B. Correct answer is unstable development. So we see that here this excessive uncontrolled abstraction, the aquifer deterioration is irreversible, and there's a huge conflict between stakeholders. So the correct answer is option B, unstable development. Now, which type of groundwater modeling occupies an intermediate position between distributed and black box model? We talked about three models: black box, lumped, and distributed. Which one is occupying an intermediate position out of this: black box, lumped, distributed, or artificial recharge models? So yeah, the correct answer is lumped models. It's in these black box models, distributed models, and lumped models. Lumped models is somewhat an intermediate between these two because it will consist of statistical as well as physical based methods. Next question. So the correct answer is option B. Now, which stage of groundwater resource development is indicating that the groundwater extraction is rapidly expanding with some impacts on the natural regime and strong dependence of various stakeholders on the resource? Is it the baseline situation, incipient stress, significant stress, or stable, highly developed stage? Okay, so the correct answer is option B. Stable, highly developed stage is when everything is in a good state. I mean, there is extraction, but it is not impacting the groundwater resources, or there is no conflict or anything. The significant stress, there is we'll go here. The first one is baseline. Second is there is an increase in the aquifer and small conflicts. Significant stress is when the abstraction is rapidly expanding and it is starting to impact the natural availability of groundwater or the flow or whatever it is associated with the groundwater. Such a stage of development is called significant stress. So the correct answer would be option B. Which organization in India is responsible for regulating groundwater developments? Correct answer is Central Groundwater Authority, as the name suggests. Now, groundwater pollution can occur due to the mixing of which of the following substances: fresh water from rivers, rainwater from precipitation, oil, gasoline, and pesticide, condensed water vapor from the atmosphere. Correct. The answer is oil, gasoline, and pesticides. So that was the end of assignment 10. Like I said last time, I'll be starting revision of the week one, week two in the subsequent section. So today we'll start with the assignment one questions. There won't be much explanation because we have gone through all of these portions in the earlier problem solving sessions, plus the lecture materials and videos are all available. So we'll just go through the question, try answering most of it, and then you'll have the PDF and video also with you. So these are problems that comes in the first assignment. Which phase of the hydrological cycle is involving the movement of water from the surface into the ground? Is it transpiration, precipitation, infiltration, or evaporation? So the correct answer is option C, infiltration. We know what transpiration is. Transpiration is the movement of water from plants. Plants take up water from the soil and then it will travel through the plants onto the leaves and it goes out from the leaves, evaporates. So you can say it transpires out of the leaves. Precipitation is nothing but rain or snow. It is coming from the atmosphere onto the earth's surface, onto oceans, everywhere. Evaporation is the uh, component where water is moving back from the earth's surface, from the surface of oceans, from the surface of buildings or whatever. It is changing from the liquid form to the vapor form and going back into the atmosphere. So these are some of the basic hydrological components involved in the hydrological cycle. Next one is, what is the term for water that flows over the surface of the land into streams and rivers called? Is it groundwater flow, precipitation, runoff, or infiltration? Yes, pretty simple question. The correct answer is option C, runoff. Groundwater flow is the flow that is occurring below the surface, the lateral flow, groundwater, or so we can also call it as base flow. Sometimes interflow is also no, interflow is not groundwater. Base flow is groundwater flow. Question 3. Process by which water is absorbed by plants and then released to the atmosphere is called as, just now we discussed it. Correct. Transpiration. Now, what is the term for the process in which water is moving directly from the solid to the gaseous phase called as? Okay, it's called sublimation. Sublimation is the change in phase of water directly from solid to gaseous state. Condensation is the when water changes from uh, water vapor gaseous state to liquid state, it is called condensation. And evaporation is when water changes from liquid to vapor. Next question, what proportion of the earth's water is fresh water? Correct answer is option C. So we see that 96 or 97 percentage is covered with salt water, and 3 percentage, around 3 percentage is covered with fresh water. In fresh water itself, glaciers and ice caps are covering around 68.7 percentage, 30 percentage is groundwater, and it is only around 1.2 percentage that is rivers, lakes, ponds, and all. Even in 1.2 percentage, ground ice and permafrost is occupying the major percentage. Lakes come second, and it is rivers and all are only forming 0.49 percentage of the fresh water. So this is the major source of water that we have. So it is very important that this is the only amount of water that is available, but is maximum utilized, indicating the importance of preserving these water sources. Now, water budget equation. What is the water budget equation? Which out of these following options depicts the water budget equation correctly? Okay, so the correct answer is option B. Change in mass storage is equal to inflow minus outflow. So here it is just twisted a bit, rearranged a bit and given. So inflow minus outflow is equal to delta S. That is the water budget equation. So here the option B is what is depicting it correctly. Again, water budget equation with the components, which out of the following is the correct representation. Okay, so the correct answer is option C. P is the precipitation, which is a inflow component. Runoff, groundwater flow, evaporation, transpiration, all of these are outflow components. So you know inflow minus outflow is what is the change in storage. So inflow minus these four components which are outflow will be the correct answer. Now these are numericals that will come. I mean, I've selected out every pattern of numerical that is possible in this first assignment that has probability to come. So if you can do it, it will be beneficial for you for the final exams. Precipitation in area is 800 mm, runoff is 50 centimeter. Calculate the evaporation. Simple numerical. Again, just follow the principle of water budget inflow outflow. So here again, evaporation is the precipitation minus runoff. So considering there's no other component that is given, so just minusing 800, I mean finding the difference between 800 and 50 centimeter is given here. So you have to convert it to mm. So it is 500 mm. So it will be 300 mm is the correct answer. Here they've asked to find the change in storage. If the seepage loss is 30 mm, precipitation is 20 centimeters and evaporation is 10 centimeters. This requires using the water budget equation in its proper form. So do find out the answer. I'll be only going to the solution once I get the answers in the chat box. Okay, so the answer for this goes like this. Here the inflow component is precipitation, which is in 20 centimeter, and the outflow components are seepage loss and evaporation. Here seepage loss is given in 30 mm, so if you convert it to centimeters, it becomes 3. So 10 plus 3 is 13. 20 minus 13 will be 7 centimeters. But since we require the answer in meters, we convert it to meter to get 0.07 meters. Simple arithmetical problem, you can do it only, you can do it just by knowing what is inflow, what is outflow, and the water budget equation. Now, this is the last and the final question for this week's session. This is a numerical, again, that is based on the water budget equation. Here, although it is the rate that is given, so you have to do conversion of the quantities into volume before finding out the answer. You can do this and post it in the chat box. They give it the initial storage as 17.5 hectare-meter. Since the final answer is required to be in meter cube, we need to convert it to meter cube. So 1 hectare is equal to 10 to the power 4 meter square. So you will get 17.5 into 10 to the power 4 meter cube. From there, they are giving us a duration, 3 hours. So that what would be the storage in the reach after an interval of 3 hours if the average inflow is this much and outflow is this much. So we convert this 16.2 and 12.6 into volume by multiplying it with the duration. After that, by making use of the water budget equation, you can easily find out the answer. So let's just go. Correct answer is option C. This is how. Initial storage is 17.5 hectare-meter. So converting it into meter cube, we'll get this quantity. Inflow rate is given as 16.2 meter cube per second. So when you multiply 16.2 into 3 hours into 3600, that is converting this hours into seconds, we get this quantity as the inflow volume. Similarly, outflow rate is given. When we convert it to the outflow volume by multiplying it with the duration of the time and converting it to seconds, we get this quantity. Final storage is equal to change in storage is equal to inflow minus outflow. So here we have 17, this quantity minus this quantity will give us the change in storage. Change in storage is nothing but the final storage minus the initial storage. We have the initial storage, we have the change in storage. So from this you can find out the final storage, which will be this quantity. So this was the final question for today's session. If you have any doubts regarding the session today, you can you feel free to ask. Otherwise, you're free to leave the session. Thank you for attending today's session and participating in answering the questions. We'll see next week, same time with assignment 11 related problems as well as revision of probably assignment 2 and assignment 3. Thank you.